Welcome back. In this lesson, we're going to go over section 18B, mean of a distribution in your SL textbook. So from the last lesson in 18A, we looked at what is a probability distribution. Basically, it is a summary of what happens when you carry out a probability experiment or like look at the theoretical probability of an event, and then listing out all the possible probabilities. But after we have listed them out, we probably want to look at, well, what is the general behavior of a certain distribution? Therefore, we look at something called the expectation of the distribution, or sometimes this is called E of X, the expected value. What it really does is it look at the mean, the average, okay? In IB, they use the symbol mu to show this value. So to calculate the mean or expectation of this probability distribution, we use the formula by summing up basically the value of X times the associated probability of every single X values in the distribution itself. So because this is just an average value, it is possible that even though when we are talking about discrete variables X, we could end up with a decimal number, say 3.8 fish in a pond, because it is just an average. So let's take a look at an example. So a robot is in the process of shooting 2 high goals. If the probability of success on each shot is 0.7, what is the expected number of points scored? So let's let X to represent the number of points scored. You can only do discrete, right? 0, 1, or 2 goals. So let's take a look at each time the robot shoots a goal. It can either be successful or fail. It fails the shot, right? It misses. So using a tree diagram, we can list out, the whole sample space. The first trial, success has a probability of 0.7, fail would be 0.3, right? They're complementary. When the robot makes a second shot, if it was successful the first time, it may be successful or it may fail in the second shot. So again, we put the weight of these probabilities on the branches. If the robot failed the first shot, it can either still be successful the second time or it misses. Okay, so here is the entire tree diagram. In order to process that expected value, it would be worthwhile to actually lay out the probability distribution again. Thinking that the robot is making 2 shots, what could really happen is it misses both, so it doesn't score any points. So X could be 0. It scores 1 point in the case of fail then success or success then fail. So X can be equal to 1, making 1 shot, or it is successful in both shots. So X could also equal to 2, scoring 2 points. Once we have laid out all the possible values of X, then we can calculate the probability associated with each X. Following the tree diagram, getting no points is a fail times a fail. So these are independent events, right? So we multiply these probabilities, 0.3 times 0.3. Making 1 shot, it can either be it's successful and then fail, or we can include a case where it first fails but is successful after. So 2 cases added together, you multiply those probabilities, it's equal to 0.42, or the robot scoring 2 points in the case of success followed by another success, so that's 0.7 squared. The third column is basically a column that we use to process or to calculate the mean value, because we need to find out the individual product of the value of X times the associated probability. So in the first row, multiply the first 2 columns together, 0 times 0.08. In the second row, multiply 1 by 0.42. In the third column, we multiply 2 by 0.49. And then remember, we add these numbers together in order to come up with E of X, the expected value, or the mean of the distribution, which results in 1.4. To interpret the meaning of this number, we say that over time, the robot will score an average of 1.4 goals. So that means if the robot keeps shooting, and then you track the number of points it scores each set of 2 shots made, it will have result in 1.4 goals. Second example. So we have this probability distribution table in column form. For this particular random variable x and the probability distribution given, we're going to find the mean, median, and mode. So let's start with completing maybe the table first. So notice how we have added a column called the cumulative probability. If you recall your statistics lessons back in chapter 16, chapter 17, you have also calculated something called a cumulative frequency for a histogram. So basically it's the same idea, right? You're starting from your first group. The probability of scoring x equals 0 is 0.1. And then you start accumulating. So the probability of x being equal to 1 or less than 1, right? Because it includes all the groups, is 0.25. The next row, you add the first 3 probabilities together. So the probability that x is equal to 2 or less is 0.55 and so on. And it should not be surprising that when you reach the end of your probability distribution, your cumulative probability would be equal to 1 because you should have covered every single possibility in this probability distribution. And then the last column, again, is the working column for us to use for finding the expected value or the mean of the probability distribution. So once again, the formula is to add x times p of x. So that means we're multiplying the first column to the second column. So 0 times 0.1 is 0, 1 times 0.15 is 0.15, 2 times 0.3 is 0.6, and so on. And then you can add them up, these numbers, to get 2.15. So let's list out what's going on here. So we have found using the very last column that the mean, the expected value, or the sigma, the sum of x times px, same thing, is equal to 2.15. The mode, another measurement of central tendency. The mode is the score with the greatest probability of success, right? The most frequent x value. Well, you just have to go to the second column and look for the highest probability shown, which is 0.4. So that means the mode is 3. 3 is the value that happens most often. And then the median is referred to as the 50th percentile score. So that means when you rank everything in order, it's going to be right in the middle, right, of your data set. So the value of x that's occupying the middle position of your data set. In a sense, this is like looking at the cumulative probability, right? Because we're going from the least to the greatest. And then the 50th percentile should be the 0.5 cumulative probability. While even though 0.5 does not show up in this column, we know that it is between 0.25 and 0.55, and it should be more likely to be in the 2 section, right? Because like by the end of all the ones, we have only reached 25% of the probability distribution, so it must fall under 2. So the median here is 2. Next example. So discrete random variable y has this particular probability distribution. So this is a very typical IB type question that you'll see. So they will give you a probability distribution with some missing values. So part A, you're going to find the exact value of k. Well, knowing that if I add up all the probabilities in the probability distribution, what does that have to equal to? Right, it has to equal to 1. So that means I can set up an equation then to say that, well, if I add k plus 2 over 5 plus 1/4 plus 2k, that must equal to 1. And you can solve this equation and look for the value of k. So now I know what k is equal to. In a sense, I can now fill it in. So when y is equal to 2, the probability of getting that is 7/60. And then also in 5, when y is equal to 5, the probability of getting a 5 in this case would be 14 over 60. These values will be useful when we calculate the expected value of y, because that calls us to, okay, let's find the sum of y times py for values of y ranging from 2 to 5, right? So essentially this is like the more algebraic substitution format than how we just work out each individual entry of y times p and then we add it all up like in the previous examples, okay? But it's really the same thing. So you multiply 2 by k, which is 7 over 60, plus 3 times 2/5 plus 4 times 1/4 plus 5 times 14 over 60, and then works out to 18 over 5, which is 3.6. And remember, because this is just a theoretical average, even though these y values represent discrete numbers, it's okay for the e of y value to be a decimal. Okay? And that's it for lesson 18B. So here are the homework that you can do to practice